Example 1.3, a 50-kilogram circular piston shown in the figure floats on 0.12 moles of compressed air. A, how many nitrogen and oxygen gas molecules are in the gas? B, what is the piston height H1 if the temperature is 300 degrees C? We'll call that state 1. Now, the temperature of the air is increased by 100 degrees C, which I'll call state 2. What type of thermodynamic process takes the gas from state 1 to state 2? Explain your reasoning. Draw a sketch and a PV diagram of the situation. What is the height change of the piston? A. To calculate the number of N2 and O2 gas molecules, note that air is composed of 78% N2 gas and 21% O2 gas. So it's a percentage. So from the number of moles, so from the mole number of air, this tells us then that if the mole number of air is 0.12 moles, then this tells us then that only a percentage of them are nitrogen gas. So that means then the mole number of nitrogen gas is then 78% of that times that of air, which then gives us a value of 0.0936 mole. And then the number of O2 molecules is 21% of that of air. And that gives us a value of 0.0252 moles. So from that, we could immediately calculate the number of oxygen and nitrogen molecules. So the number of N2 and O2 gas particles goes as follows. Well, I know that the number of moles is equal to the mole number of nitrogen gas is equal to the number of gas molecules divided by Avogadro's number. So then if I just do the algebra and put in my numbers, I'm then going to calculate that this is 0.0936 mole times Avogadro's number, which is 6.022 times 10 to the 23, and this will be molecules per mole, and you could see that these moles are going to cancel out. Then I'm going to have a number that's equal to 5.64 times 10 to the 22 N2 molecules. And that's going to give me that right there. So I now know what it is for nitrogen. To get oxygen, I'm going to follow the exact same process. So that means then that the number of O2 is going to be the mole number times Avogadro's number. And if I plug in my numbers, I get 1.52 times 10 to the 22 O2 molecules. So now I have completed part A. So now if I come back up here, they're asking what is the height H1 if the temperature is 30 degrees Celsius? And this is what we call state 1. So let's look at this thing. So when I look at this case here, so the height of the piston head is determined by the gas pressure inside. And of course, this is given by the ideal gas law. So when I look at that, it's this pressure inside times the volume of the piston that's going to equal to nRT. So we know what the temperature is, we know the number of moles, and we're trying to find the volume to get that height. So what we have to do is that we must compute this first. So let's go and compute this. So the one thing that we want to pay attention to here is that when I look at my piston, they said something very specific. And they said this: the piston head is floating. And if the piston head is floating, that implies that it's in static equilibrium. And if it's in static equilibrium, that further implies that the pressure inside must equal the pressure outside. That's what we got to pay attention to. So now let's draw a piston head. So let's say that this is our piston head right here. So here's our piston head right here. And then inside, we have this compressed air. So what you're seeing here is that this guy right here is our piston head. And what we're finding here is that we have two pressures that are playing. So we have the pressure from the gas inside pushing up, and then we have the pressure from the outside pressing down. And so when I look at this thing, here's what we're seeing here. We know that the diameter of the piston, they said it's a circular one. So we know that the diameter is 10 centimeters. So that means its radius is 5 centimeters. And it's this height that we're actually trying to calculate. So this is H1, and this is what we're trying to calculate. So what do I know? Well, if I look at the pressure inside, so the pressure inside is given by the ideal gas law. So that has to be the pressure of the gas, where we've already showed here that the pressure of the gas is the volume times nRT. So in this case, this is the volume 1 and this is the temperature 1. And when I look at the pressure outside, there are two contributions. There's the pressure due to the atmosphere pushing down, plus the pressure due to the piston head. And what I mean by this here is that this piston head has weight. So the weight of the piston head adds pressure on the gas. So now our job is to calculate that. So let's go calculate the pressure. Here we go. So the first thing I'm going to do here is that I need to calculate the outside pressure. So if I calculate the outside pressure, it should be written like this here. So I know that the outside pressure has to equal the pressure of the atmosphere, which is well-known value. And then this is going to be the pressure due to the weight of the piston head. So if I look at this thing, then P atmosphere, we already know what it is. But when I look at the pressure due to the piston head, it's got to be the weight of the piston head divided by the area. Now, we know a couple of these numbers already. We know that the mass of the piston head is 50 kilograms. And we know that the area, because it's a cylinder, must be pi r squared times the height will give me the volume, where r is equal to 0.05 meters. In other words, 5 centimeters. So now I'm going to punch in my numbers here. So if I punch in my numbers, the atmospheric pressure is 1.01 times 10 to the 5 pascals. Then I'm going to get the mass, the weight. So it's got to be 50 kilograms times 9.81 meters per second squared. And this is all divided into the area, which would be 0.05 meters squared. So if I compute that, I get a value of 1.64 times 10 to the 5 pascals, and that's the pressure of state 1. Okay, so I now have my pressure. So now if I have my pressure, now I'm going to use the ideal gas law to calculate the height. So then I'm right here. So now I'm going to use the ideal gas law to get the volume, but the volume V1 is the same as the area times the height 1. So let's go do that. So then I see then that here I go. So it's going to be, so the ideal gas law says it's pressure 1 times volume 1 equals nRT1. So now I'm just going to solve for the volume. So if I solve for the volume, note that it's going to be A times H1, but then I'm going to take the A to the other side. So then I have that H1 should then be nRT1 divided into P1 times A. So let's go plug these numbers in. I know that the number of moles, I know the gas constant, and of course I know the temperature, which would be 30 plus 273 Kelvin. And all of this goes into, it's divided by the pressure. And then I get pi times 0.05 meters squared. And when I compute this number, I get a value of H1 that reads 0.227 meters or 22.7 centimeters. And that is the height of the piston head. So now what we want to do here is that we want to come and get this whole thing, so we don't have to keep coming back and forth. So now let's look at the last piece of the question right here. So now we're on C. And what we see here on C here is it tells us that now we heat up the air by 100 degrees C. So it goes from 30 degrees C to 130 degrees C, which is now called state 2. And it says, what type of thermal process takes the gas from state 1 to state 2? Explain your reasoning. And then it says, draw a sketch and a PV diagram of the situation. So here we go. Okay. Because the piston head is floating, this is a constant pressure. And what do we call a constant pressure? This is called isobaric process. So that means there is isobaric heating that keeps the pressure constant. And this happens so slowly, it's so slow that this is what we call quasi-static. That means that the incremental changes are so small that it leaves the state effectively at constant pressure the whole time. So picture-wise, here's what I see. So I have state 1. So that means I have pressure 1, volume 1, temperature 1. So if I look at my piston head, it has to look something like this. So let's say that this is my piston head. And no, that's my piston, but this is my piston head. So here's my piston. And then here's my gas right here. And what I know here is that the only thing that's going to change is, according to this, is the volume and the temperature. So you could see here, I'm going to be heating this thing up. So when I have this heat, what ends up happening is that heat flows into the piston container that has the gas. So I know at this point, you can see I have a smaller volume and I'm going to have a low temperature. But I heat this thing up. And as I go through this isobaric process, what happens here is that my piston head rises. It goes to, let's say, this height right here. So as it goes to this height, what you're seeing here is that heat continues to flow into the system, but now, because all this heat is coming in, I have a bigger volume and it goes to a higher temperature. So when I look at this state 2, I know that P2 is the same as P1, but now I have a bigger volume and a bigger temperature. So when I look at this thing on a PV diagram, it looks something like this. I'm going to move this over here just to conserve some space. So when I look at my PV diagram, it has to look something like this. So here's my state 1. Here's my state 2. And my process goes like this. It goes straight across this pressure volume diagram. And you could see here that I have P1 here, V1, T1, And then over here, I have the same pressure, but a bigger volume and a higher temperature. And the only way that could be the case here is if I add heat. That's the only way I could do that. So now from the ideal gas law, we write this thing here. So from the ideal gas law, we see that the pressure has to be a constant. But according to the ideal gas, it's going to be nRT divided by V. Now note, because this is an enclosed container, the number of moles are fixed, and of course the gas content is a constant. So what this really tells me here, that I can connect the temperature and the volume of one, but in order to keep this a constant, if I increase the temperature, then the volume has to increase at the exact same rate. This is the isobaric condition. In other words, if you increase temperature, you have to increase volume at the exact same rate. So in essence, this is a knife's edge that you're really looking at. Because if you don't increase it at the same rate, then it's not isobaric and it's not constant pressure. So now moving down here, I'm now going to go in and I'm going to use this thing here. So now I'm going to use this isobaric condition to calculate the new height of the piston head. So if I do that, that tells me then T1 over V1 has to be T2 over V2. Now I'm going to solve for V2. And as I solve for V2, you could see that this guy's going to be T2, T1, V1. But that really means what? That this is really the height 2 has to be T2, T1, H1, where the areas cancel. So now I'm just going to put in my new values. So here we go. So my new values go like this. It's I start off, I go to 130, 273, and then I started off at 30, 273, and we already know that the old height was 0.227 meters. So when you compute this number, I get a value of 0.302 meters, which is H2. So now the height change is then going to be delta H, which will be H2, H1, which will then be 0.302 minus 0.227, and then I get 0.075 meters or 7.5 centimeters for delta H.